Imagine a world where the familiar rules of physics cease to exist. A world where objects can be in two places at once, where information travels instantaneously across vast distances, and where particles effortlessly pass through seemingly impenetrable barriers. This is the captivating realm of quantum mechanics, a field of physics that governs the behavior of matter and energy at the atomic and subatomic levels. This strange and counterintuitive world challenges our everyday understanding of reality. It's a world where particles behave like waves, and waves behave like particles. It's a world where the act of observation can influence the very nature of what we observe. The quantum world is full of mysteries and paradoxes, but it's also a world of incredible beauty and elegance. By unraveling the secrets of quantum mechanics, we can gain a deeper understanding of the universe and our place in it. The journey into the quantum realm is an adventure into the unknown. It's a journey that will challenge our assumptions and expand our horizons. It's a journey that promises to revolutionize our understanding of the universe and everything in it. The seeds of quantum mechanics were sown in the late 19th century, a time of great scientific curiosity and exploration, and early 20th centuries. Physicists were grappling with phenomena that classical physics couldn't explain, leading to intense debates and experiments. One such puzzle was blackbody radiation, the light emitted by heated objects which seemed to defy the existing laws of physics. Classical physics predicted that the intensity of this light should increase infinitely at higher frequencies. However, experiments showed otherwise, creating a significant dilemma. In 1900, Max Planck proposed a radical solution. Energy is not continuous but exists in discrete packets, or quanta. This was a groundbreaking idea that challenged the very foundations of physics. This revolutionary idea marked the birth of quantum mechanics, opening up a new realm of scientific inquiry and understanding. Albert Einstein further solidified the concept of quanta in 1905, with his explanation of the photoelectric effect, a phenomenon that puzzled many scientists of the time. He showed that light too behaves as if it were made up of particles, now called photons, which interact with matter in quantized ways. Niels Bohr applied quantum theory to the structure of the atom in 1913, proposing a model that would revolutionize our understanding of atomic structure. He proposed that electrons orbit the nucleus at specific energy levels, a concept that was both innovative and controversial at the time, and that light is emitted or absorbed when electrons jump between these levels, a process that explained the spectral lines observed in experiments. This model, although groundbreaking, was incomplete. It couldn't explain the behavior of more complex atoms, leaving many questions unanswered. It couldn't explain the behavior of more complex atoms, leading to further research and discoveries in the field of quantum mechanics. In the 1920s, Werner Heisenberg introduced his uncertainty principle, a concept that would become a cornerstone of quantum theory, which states that it's impossible to know both the position and momentum of a particle with perfect accuracy, a principle that has profound implications for our understanding of the microscopic world. This principle, along with Erwin Schrödinger's wave equation, laid the foundation for modern quantum mechanics, providing a mathematical framework for the behavior of quantum systems. Schrödinger's equation describes the behavior of quantum particles as waves of probability, a concept that challenges our classical intuitions, suggesting that particles don't have definite positions until they are observed, a notion that continues to intrigue and perplex scientists to this day. To truly grasp quantum mechanics, we must venture into the heart of matter, the subatomic realm. This is a world so small that it defies our everyday experiences and challenges our understanding of reality. Here we encounter a fascinating cast of characters that make up the building blocks of our universe. These particles are the fundamental constituents that form everything we see, touch, and experience. At the heart of every atom lies the nucleus, composed of protons and neutrons. This dense core is incredibly small, yet contains nearly all the mass of the atom. Protons, positively charged particles, determine the element to which an atom belongs. For instance, an atom with 1 proton is hydrogen, while an atom with 6 protons is carbon. Neutrons, on the other hand, carry no charge and help stabilize the nucleus. They play a crucial role in the stability of atoms, especially in heavier elements. Orbiting the nucleus are electrons, negatively charged particles that are much lighter than protons and neutrons. These electrons form a cloud around the nucleus and are responsible for the atom's chemical properties. These tiny particles are responsible for the chemical behavior of atoms. The way electrons interact with each other determines how atoms bond to form molecules. The interactions between electrons in different atoms are what allow for the formation of molecules and ultimately, all the matter we see around us. This is the foundation of chemistry and biology, but the story doesn't end there. The subatomic realm is even more complex and intriguing. Protons and neutrons are not fundamental particles. They are composed of even smaller particles called quarks, which are held together by the strong nuclear force. Quarks come in 6 different flavors: up, down, charm, strange, top, and bottom. Each type of quark has unique properties and plays a specific role in the structure of matter. Protons are made up of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. This combination gives protons and neutrons their distinct characteristics. Along with quarks, there exists another family of fundamental particles called leptons. These particles are essential to the structure and function of the universe. Electrons are a type of lepton. They are crucial for the formation of atoms and the chemical reactions that sustain life. Other leptons include muons, taus, and their corresponding neutrinos. These particles are less familiar but equally important in the grand scheme of the universe. Finally, we have bosons, particles that carry forces. These particles are the mediators of the fundamental forces of nature. The most familiar boson is the photon, the carrier of the electromagnetic force. Photons are responsible for light and all electromagnetic radiation. Other bosons include gluons, which carry the strong force, W and Z bosons, which carry the weak force, and the Higgs boson, which is associated with the mechanism that gives particles mass. Understanding these particles and their interactions is key to unlocking the mysteries of the universe. The subatomic realm is a fascinating and complex world that continues to captivate scientists and researchers. Section 4. The Enigma of Quantum Principles. Quantum mechanics is built on a set of principles that defy common sense. These principles challenge our understanding of reality and push the boundaries of what we think is possible. These principles, though strange and counterintuitive, have been repeatedly confirmed by experiments. Scientists have spent decades testing and retesting these ideas, and the results consistently support the quantum view. One of the most mind-boggling principles is wave-particle duality. This concept fundamentally changes how we understand the nature of particles and waves. This principle states that particles, like electrons and photons, can exhibit both wave-like and particle-like behavior. Depending on the experiment, they can act as discrete packets of energy or as continuous waves. In some experiments, they behave like tiny balls of matter, while in others, they act like waves spread out over space. This duality is a cornerstone of quantum mechanics and has profound implications for our understanding of the universe. Another key principle is superposition. This principle is one of the most fascinating and perplexing aspects of quantum theory. In the quantum world, particles don't exist in definite states until they are measured. Instead, they exist in a superposition of states, meaning they can be in multiple states at once. This idea challenges our classical understanding of reality. Instead, they exist in a superposition of states, meaning they can be in multiple states at once. This concept is often illustrated by the famous thought experiment known as Schrödinger's cat. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, a quantum particle can be in a superposition of different states until it is observed. Similarly, a quantum particle can be in a superposition of different states until it is observed. This observation collapses the superposition into a single state. Entanglement is perhaps the most bizarre and intriguing quantum phenomenon. This phenomenon suggests that particles can be connected in such a way that the state of one particle instantly influences the state of another, regardless of distance. When two particles are entangled, their fates are intertwined, no matter how far apart they are. This connection persists even if the particles are separated by vast distances. If you measure the state of one entangled particle, you instantly know the state of the other, even if they are light years away. This instantaneous connection defies our classical understanding of space and time. This spooky action at a distance, as Einstein called it, seems to violate the principle of locality, which states that nothing can travel faster than light. Yet, experiments have repeatedly confirmed the reality of entanglement, adding to the enigma of quantum principles. Section 5. Quantum Mechanics in Action. Quantum mechanics might seem like an esoteric theory confined to the realm of theoretical physics, but its impact on our daily lives is undeniable. From the smartphones in our pockets to the lasers scanning groceries at the checkout, quantum mechanics is the invisible force powering countless technologies we rely on. Take electronics, for instance. The transistors that form the backbone of our computers and smartphones rely on the quantum mechanical behavior of electrons in semiconductors. Without quantum mechanics, our digital world would simply not exist. Quantum computing, an emerging field with the potential to revolutionize computation, harnesses the principles of superposition and entanglement to perform calculations that are impossible for classical computers. Quantum computers could one day lead to breakthroughs in medicine, materials, science, and artificial intelligence. Medical imaging is another area where quantum mechanics plays a crucial role. Magnetic resonance imaging, or MRI, uses the quantum properties of atomic nuclei to produce detailed images of the inside of the body. Positron emission tomography, or PET scans, which detect diseases like cancer, also rely on quantum mechanics. Even the Global Positioning System, or GPS, that guides us to our destinations wouldn't be possible without quantum mechanics. GPS relies on atomic clocks, which use the precise frequencies of atomic transitions to measure time with extreme accuracy. Section 6. Unraveling the Quantum Mysteries. Despite its remarkable successes, quantum mechanics is still riddled with unsolved mysteries and open questions. One of the biggest challenges is unifying quantum mechanics with general relativity, Einstein's theory of gravity. These two pillars of modern physics seem to be incompatible at the most fundamental level. Another major mystery is the nature of reality itself. Quantum mechanics suggests that the act of observation plays a crucial role in determining the outcome of experiments. This raises profound questions about the nature of reality and the role of the observer. Does the moon exist when nobody is looking at it? Quantum gravity, a hypothetical theory that seeks to unify quantum mechanics with general relativity, remains one of the most sought-after goals in theoretical physics. Such a theory could potentially explain the origin of the universe and the nature of black holes. Dark matter and dark energy, two mysterious entities that make up the vast majority of the universe's mass and energy, also pose significant challenges to our understanding of physics. While their existence is inferred from their gravitational effects, their true nature remains elusive.
Don't forget to like, share, and subscribe for more content like this. And remember, you are valuable.